morning, friends. It gives me immense pleasure to be here for my lecture, that is of the flight mechanics for 4th semester aeronautical students. And we have today the main topic is point mass model and the dimensional analysis. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. The today's lecture topics are point mass model, George Cayley explanation, dimensional analysis, Reynolds number, Mach number. This I am going to discuss because it is very much important for any aeronautical student to understand this concept. They are the basic concept. If you do the wind tunnel testing or the computational fluid dynamics, you have to understand that if you have a very big aircraft, you cannot test inside the wind tunnel. You need some method by which. So the dimensional analysis, which will make some non-dimensionalization of some numbers, those numbers are very useful in aeronautics. Like two numbers are very important, that is the Reynolds numbers and the Mach number. This we will be going to discuss today, and we will also see the point mass and the George Cayley explanation for the lift. So we will see here that in the previous class we have discussed about excess power, power available, power required, effect of altitude, absolute ceiling. These all things we have already done. In the last class we have also discussed about range and some other parameters of the aircraft, for the range for the propeller aircraft, range for the jet aircraft. Also we have seen the absolute ceiling, effect of altitude, and so many things we have already covered. So now we will be discussing today the point mass model. And why we require the point mass model? Because in a very big aircraft, there are millions of points. We have to consider one point which can represent your whole aircraft. Mostly we take at the center of gravity or the center of mass as the point. And if we assume that that center of mass is moving with respect to the aircraft is constant, we can assume that point mass system is a workable solution. So point mass models are useful to investigate the local and the global properties of the flight path. That is to say, the point and the integral performances. They allow us to determine the control values to obtain optimum flight conditions. For example, defining the navigation law to obtain the maximum endurance. Center of mass or the center of gravity has to be determined for the aircraft. The CG of the aircraft should lie just before the main landing gear. Behind the landing gear is not good, as tail may touch the ground during the takeoff. If CG is more vertically offset, then nose up or down tendency will be there. After deciding the CG, equation of motion can be derived by Newton's law of motion, considering mass as the center of gravity by F. So if this is the aircraft, okay, this is the aircraft. So we choose some, and this is called the center of mass and center of gravity. So if our landing gears, always we should have little ahead. So here, this is the landing gear. This is the landing gear. If it is ahead, it is always good. If the CG is, it should be always in between. If it is behind, then it will create the nose down or the nose up tendency, and aircraft will not be in a good position. So we consider that the total mass of the aircraft is acting at the center of mass or the center of gravity. By this, we are able to derive the equations of motion by using the second law of Newton's second law of motion. Now, we will see the method of lift analysis. So here we have the component build-up method, CFD method, and the wind tunnel testing. So how we can test the lift analysis? We can use the component build-up method, means we have to make a component, then we have to test it. Then we can use the CFD method, a computational method, or we can use the wind tunnel testing. Before that, we will see that how this Judge-Cayley lift concept was developed. If there is an angle between the plate, this red color is a plate. This is the plate. This is the plate. This, I think, this you can see. I am just making here somewhat bigger. This is the plate, and this plate is moving here with the velocity v as shown here. It is a v vector, and there is an angle between this. So this always, there will be a force which is perpendicular to this P, perpendicular to this plate, that is the R. There will be one force which is perpendicular to the velocity vector, and that is the lift. This is the lift. And there is one horizontal force which is opposing this. This is called the drag here. So here we can say this is the drag, this is the lift, and this is. So Judge-Cayley has explained that if any plate, you take any plate, and if it start moving with this velocity v, like this, and if there is an angle this alpha, there will be a lift in the vertical direction, and there will be a drag in the same direction of the motion. So this concept was developed by the Judge-Cayley. And after that, we have seen that our lift, the aerodynamic forces and this other forces are not acting in fact in the same point. So if you see here, there will be a rotation between this and this. So normally this weight will act in the center of gravity, and your thrust will also act here. Drag and this thing will act at the aerodynamic center. So this aerodynamic center, we have to assume that if we assume as a constant, then we have to add one moment that is called the CMAC. So lift and drag, and there will be always one moment, and this moment will make the pitching up and the down. So this concept we have to understand very well. Now we will discuss about Buckingham's pi theorem. This theorem was very useful for dimensional analysis, and this is also very useful for aircraft motions and all. Buckingham's pi theorem states that if a quantity q naught, a dependent variable, is completely determined by the value of a set of n independent quantities, of which a number k form a complete dimensionally independent subset, then a suitable dimensionless q naught will be completely determined by n minus k dimensionless. Okay, so these many equations will be there. So here we can see again that it is a plate is moving with velocity v and angle is theta. This is the lift, this is the r, and this is the drag, this is the weight. So here this lift is a function of angle of attack alpha, area of the plate, velocity of the plate, and the density of this air, shape, viscosity, compressibility. This compressibility is dependent upon the Mach number, and if the Mach number is 1, it is called the subsonic. Mach number is 1 is called the sonic, and if Mach is greater than 1, it is called the supersonic. So it becomes a Herculean task to do testing by varying each parameter. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It is very difficult to do these all things. So if we have some non-dimensional number, and if we make that thing constant, we can do the testing very easily. So here we will see that how we can perform this non-dimensional numbers, how we can get it, okay, Reynolds number and the Mach number. So we know this lift is equal to function of velocity, density, area, Mach number and the viscosity for a given angle of attack. We can write L is equal to Z, V to the power A, rho to the power B, S to the power D, A to the power E, mu to the power F. So here Z, we can take here rho, V square S. Here we will divide A by V here, A by V to the power E, plus here mu by rho Vs to the power 1 by 2 to the power F. So here if you see rho by mu by rho Vs to the power half is equal to 1 by Re. Re is a Reynolds number. So this Re is equal to rho VL, S is area, so here only one, so rho VL by mu, and here A and V is called the 1 by Mach number, so it is 1 by M. So here these two things are the constant, so lift is equal to Z, rho V square S, and these things we can call as a constant number, so it is called the CL, where this CL is equal to Z, 1 by M to the power E and 1 by Re to the power F. So we can write that this coefficient of lift is equal to function of alpha, Re and the Mach number. So now only 3 parameters are there, and these 3 parameters, if the velocity is very less, M can be neglected, this can be neglected. So your CL is a function of alpha and Re for the low speed aircraft. So if I have geometrical similar body, then I need to do limited number of experiment. For subsonic flight, M is not needed. So here we can write the CL is a function of alpha and the Re. So only these 2 parameters you can vary and you can get all the result. So that is the importance of this non-dimensionalization of the systems. So modeling of coefficient of lift, that is the dimensional analysis. So we have seen that major force in aerodynamics is a lift, which is half rho V square SCL. Now dimensional approach is needed to form the mathematical model. Let us appreciate the insight and feel the model structure. Which L or the CL we have to take? We have to take the lift or the coefficient of lift. So CL is a non-dimensional parameter. So we should try to take the CL, and this CL is a function of the alpha. And here if this is the alpha and this is the CL, for the cambered airfoil it will go like this. So this is the relation with alpha and the CL. So non-dimensional analysis of lift, drag and the moment. So lift is equal to L, D is equal to M, and D is equal to drag, and M is equal to moment. And these are the function of V, velocity, density, area, Mach number and the viscosity. And the same way, if you see here, A, V to the power A, rho to the power B, S to the power D, A to the power E, mu to the power F. And if you do the non-dimensionalization of each and every one, lift is equal to a force, it is a ml t to the power minus 2, and here V is equal to lt to the power minus 1 A, rho is equal to ml to the power minus 3 to the power B, area is equal to L square to the power B D, and here is velocity lt to the power minus 1 to the power E, ml t to the power minus 1 and F. So if we take the first term mass, so mass here is a 1, so 1 is equal to B here 1 and here is a 1. So here B plus F, so B is equal to 1 minus F. If you take the T is equal to minus 2 and here minus A, minus E and minus F. So A is equal to 2 minus E minus F, and L is equal to 1 A minus 3B plus 2B. So here D is equal to 1 minus F by 2. Putting this value, we will get L is equal to Z V to the power A, rho to the power B, S to the power D, A to the power E, and mu to the power F. So if you put this value here, we will get here L Z V2 minus E minus F, rho 1 minus F, S is equal to 1 minus F by 2, A to the power E, mu to the power F. So here rho V square S, and if you divide A by V, mu by rho V square, so you will get Z rho V square S, 1 by M to the power E, 1 by RE to the power F, where this RE is equal to inertia, is a Reynolds number, which is inertial force divided by viscous force, and here M is equal to V by A, and it is very negligible if M is equal to 0.3. So here we will get CL is equal to Z, 1 by M and 1 by RE. So this CL is a function of Mach number and the Reynolds number. These two things we got very important. So if I want to know how CL is changing with respect to alpha, M and RE, you can create a database with different Reynolds number. So a database can be created different Reynolds. Okay, so that is the importance. So in the next lecture, we will see the introduction to cruise, range and endurance, specific fuel consumption, range equation for propeller driven engine. These are the references: Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, 1999, SLY ME, Aircraft Performance Theory and Practice, AIA Education Series, AIA 2. Any questions, you are welcome to ask. I will also request you people to like and subscribe this channel. Hope this will be very useful for you. Thank you very much for the joining. Be tuned for my next lecture. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.